So, good morning. Welcome to our today's lesson. Our today's lesson is carbon and its compounds. Carbon and its compound, as you can see on the board.
Kidogo.
So, welcome to our today's lesson. Our today's lesson is carbon and its compounds. This is a very important and fertile ground in exam, and we refer to it as industrial chemistry. Under industrial chemistry, you're supposed to cover 4 elements and their compounds. The first one is carbon and its compounds, chlorine and its compound, nitrogen and its compound, and sulfur and its compounds. The first one is carbon and its compounds, and this is our area of interest during this lesson. So I'll start with, if you look at the topic, it has got 2 parts, the carbon and its compounds. So I'll start with the first part of the topic, and that is carbon. Carbon is not a new term to us. We've come across it in our Form 1 syllabus, and it's one of the elements. It's one of the elements whose chemical symbol is capital C, whose chemical symbol is capital C. In Form 2, under the topic of the structure of the atom and periodic table, we also learned that carbon is an element whose atomic number is 6. It's an element whose atomic number is 6. This means that its electron configuration is 2,4. This means that its electron configuration is 2,4. And from the electron configuration, it is an element that belongs to group 2 of the periodic table. It is an element, it belongs to group 4, of the periodic table, and it belongs to period 2 of the periodic table. So in the periodic table, the element carbon can be found in the 4th group and in the 2nd period. Carbon is an element that forms covalent bonds. It forms covalent bonds with most of its compounds. What do we mean when we talk of covalent bonds? Covalent bonds are bonds formed when there is equal contribution and equal sharing of the valence electrons so as to attain the stability. It occurs in atoms of non-metal elements of the same or different elements. So carbon from here, it's a non-metal. So once it is combining with other elements, it does so by contributing and sharing, resulting to a covalent bond. Carbon occurs in 2 forms. It can occur as a pure state or in impure states. Carbon occurs in two forms: pure state and impure state. Pure state and impure states. The pure states of carbons are the allotropes, which are the diamond, and two, the graphite. The diamond and two, the graphite. The impure form of carbon is known as the amorphous carbon. The impure form of carbon is the amorphous carbon. It can also occur in combined states. Carbon can also occur when it has combined with other substances, with other elements. It can occur as carbon dioxide, and it's found in the atmosphere. It can also occur in combined states as carbonates. It can occur in combined form as mineral oils. It can also occur in combined form as organic matter. It can also occur in combined form as organic matter, and it can also occur in combined form with other elements as carbon dioxide. So that is the occurrence of carbon. Pure state, diamond and graphite. Impure state, amorphous carbon. Combined states, the carbonates, the organic matter, the mineral oils, and with other elements as carbon dioxide. From there, we've said the first state in which carbon occurs is in pure state, diamonds and graphite. These are referred to as allotropes of carbon. These are the allotropes of carbon, and they are the next one that we are going to discuss. Allotropes of carbon. Allotropes of carbon. Allotropes of carbon. And before we look at allotropes of carbon, it is good to know what we mean with the word allotropes, allotropy, and which are these allotropes of carbon. We start with allotropes. Allotropes are the different forms of a substance in the same physical state. The different forms of a substance in the same physical state. Allotropy is the existence of an element in more than one form in the same physical state. The existence of an element in more than one form in the same physical state. That is what we call allotropy. The carbon has two naturally occurring allotropes. Carbon has two naturally occurring allotropes. And these two naturally occurring allotropes are one, diamond, and two, graphite. Carbon has two naturally occurring allotropes, one, diamond, two, graphite. And this carbon can also be manipulated using energy to form other allotropes. Allotropes called the fullenes or the buckyballs. So I'll start with the first allotrope of carbon, and that is diamond, a very fertile ground in exam. Allotrope is one of the stable allotropes of carbon, and this allotrope, we look at its physical appearance. It is a colorless, it is a transparent, and a shiny crystalline solid. Diamond, that is on its physical appearance. It is transparent, can see through it. It is a shiny crystalline solid. It is a shiny crystalline solid. How is the structure of diamond? In the structure of diamond, we've seen from its electron configuration that it has got 4 valency electrons. So in the structure of the diamond, all the 4 valency electrons, all the 4 electrons in the outermost energy level, they're the ones you're referring to, the 4 valence electrons, are used to form the covalent bonds. All the 4 valence electrons are used to form the covalent bonds, are used to form the covalent bonds. And this means that within the structure of diamond, there is no delocalized electrons. And for this reason, diamond is a non-conductor of heat and electric current. So in the examination, this is the kind of the question that you'll come across. In terms of structure and body, explain why diamond is a non-conductor of heat and electricity. Explain why diamond does not conduct heat, does not conduct electricity in terms of structure and body. And that is the reason that in the structure of the diamond, all the 4 valency electrons are used to form the covalent bonds. And this leaves it without any delocalized electrons and rendering it as a non-conductor of heat and electricity. The other property of diamond that I'm going to discuss is on its density. That's about electrical conductivity. It's a non-conductor. Reason, all the 4 valency electrons are used to form the covalent bond. The second property of diamond that I'm going to highlight on is on the density. Diamond has got a high density. It has got a high density of around 3.5 grams per centimeter cube. Diamond has a density of 3.5 grams per centimeter cube, which is high. And this is due to the continuous close packing of carbon atoms. This is due to the continuous close packing of carbon atoms. This is due to the continuous close packing of carbon atoms. Due to the continuous close packing of the carbon atoms. So again, the examiner will ask you, explain why the density of diamond is very high in terms of structure and body. And that is the correct response. We mark these statements, the continuous close packing of carbon atoms. The other property of diamond is about the melting point and the boiling point of diamond. The melting point and the boiling point of diamond. The melting point and boiling point of diamond. The melting point and boiling point of diamond is very high. Diamond has got a high melting point and boiling point of around 3700 degrees Celsius. Again, the examiner will ask you in terms of structure and body, explain the high melting point and the high boiling point of diamond. And this is the expected response, that the high melting point is due to the strong covalent bonds, which is in the giant atomic structure. The high melting point is due to the strong covalent bonds that are in the giant atomic structure. Strong covalent bonds in the strong covalent bonds in the giant atomic structure. In the giant atomic structure. Throughout the structure of diamond, we only have one type of a bond, and this bond is the covalent bonds. And when we were discussing on the structure and body, we saw that covalent bonds resort to two types of structures. A structure known as the giant atomic structure or the giant covalent structure, and a structure called simple molecular structure. Within the giant atomic structure, we have the covalent bonds existing throughout the structure, hence the name, the giant atomic structure. So it is breaking these covalent bonds requires a lot of energy. It accounts for the high melting point and the high boiling point of the diamond. Reason: strong covalent bonds within the giant atomic structure of the diamond. The other property of diamond that I'm going to discuss is on its hardness. And this is the kind of a question you find in most of the papers concerning the properties of diamond, that diamond is the hardest naturally occurring substance. Explained in terms of structure and body. So that is the next property I'm going to discuss, that diamond is the hardest naturally occurring substance. Explained in terms of structure and body. Diamond is the hardest naturally occurring substance. It is the hardest naturally occurring substance, explained in terms of structure and body. The hardness of diamond is due to the uniformity of covalent bonds between the atom. The hardness of diamond is due to the uniformity. It is due to the uniformity of covalent bonds. It is due to the uniformity of covalent bonds between the atoms, throughout the giant atomic structure, throughout the giant atomic structure, throughout the giant atomic structure. That's why it is the hardest naturally occurring substance. In terms of structure and body, explain why. Uniformity of covalent bonds between the atoms throughout the structure. From there, I'm going to request you check on the diagram of the diamond, the structure of the diamond. You've seen that it is a shiny, a transparent, crystalline solid. So how is the structure? Again, this diagram is very common in the exam. We are talking of the dots I'm drawing here represent the carbon, and each of these carbon atom is covalently bonded to other 4 carbon atoms. So if you look at this carbon atom at the middle, it is covalently bonded to other 4 carbon atoms, and the structure repeats itself in 3 dimensions. The structure repeats itself in 3 dimensions, and this is what you are referring to as the carbon atom. In between carbon atom and the other carbon atom, we have a strong covalent bond. We have a strong covalent bond. This pattern repeats itself in the 3 dimensions, and that's how we result with the giant atomic structure. This is how we result with giant atomic structure. So all the 4 valence electrons are used to form the covalent bonds throughout the structure. Hence, it's a poor conductor of heat and electricity. These carbon atoms are continuously closely packed together, and this explains the high density. These carbon atoms are strongly held together by strong covalent bonds, which is the only bond throughout the structure, hence the high melting point and the boiling point. And these covalent bonds are uniformly, the uniformity of covalent bonds throughout the structure makes it to be the hardest naturally occurring substance. It makes it to be the hardest naturally occurring substance. The other point that we're going to discuss about diamond is on its uses based on the structure. And based on the structure, what are some of the uses? One of the uses of diamond, it is used to drill. It is used for drilling purposes. And the reason why it is used to drill substances is due to its hardness. The other use of diamond is to make jewels. Diamond is used actually as a jewel to make the rings, to make the necklaces, to make the wristwatches. And this is because of its shiny appearance when polished. This is due to its shiny appearance when polished. This is due to its shiny appearance when polished. So those are the uses of the diamond based on its properties. Used to drill or to cut glass, and this is due to its hardness. We just explained why it is very hard. The other allotrope of carbon that I'm going to discuss is the graphite. It's another pure form of allotrope of carbon. That is the graphite. The graphite is the second pure form of carbon. And as I have gone through with diamond, I'll repeat the same with graphite about its appearance. This one is a black, soft, and slippery crystalline solid. This one is soft. It is a slippery crystalline solid. It is a soft and it is a slippery crystalline solid. And it's good to get the differences. The other one is said it is a transparent, it is a shiny crystalline solid. With this one, it's black, it's soft, and it is a slippery crystalline solid. The structure of graphite is made up of hexagonally arranged carbon atoms. The structure of graphite is made up of hexagonally arranged carbon atoms. Hex means 6. 6 carbon atoms are arranged to form a hexagonal layer. So the structure of graphite is such that it's made up of hexagonally arranged carbon atoms, and these carbon atoms form layer. These carbon atoms together forms a layer. It is made up of hexagonally arranged carbon atoms together in layers and together in layers. So here we have got 2 terms. We've got 2 types of bonds between carbon and carbon. That's a covalent bond. They form a hexagonal layer. The layers in turn join up with each other. So we have the bond between the hexagonal layer and another hexagonal layer, which is weak van der Waals forces. So once the carbon atoms hexagonally arrange themselves to form the layers are held together by weak van der Waals forces. The layers are held together. The layers are held together by van der Waals forces. The layers are held together by van der Waals forces. And so this is how the structure of graphite looks like. This is how the structure of the graphite looks like. It's very important to study the diagram. They are drawn. You are told to identify them. You are told to name their structures and their properties. So we are talking of the structure of graphite. And you're saying it is made up of hexagonally arranged carbon atoms. It's made up of hexagonally arranged carbon atoms. This is what you mean when you talk of hexagonally arranged carbon atoms. The shaded part, this one, represents a carbon atom. The shaded circle here represents a carbon atom. In between this carbon atom and this other carbon atom, we have a covalent bond. In between the carbon atom and the other carbon atom, we have a covalent bond. And this is what you are referring to as a hexagonal layer. This is what you are referring to as hexagonal layer. These layers to form the giant atomic structure, the layers are in turn held together by the weak van der Waals forces. The layers in turns are held together by weak van der Waals forces. The broken lines that I'm drawing here is the bond between one layer and the other layer, and this type of a bond is the weak van der Waals forces. The weak van der Waals forces. So within the graphite, we have the two types of bond, the covalent bond and the bond in between the layers, which is the weak van der Waals forces. So we discuss the properties of graphite. You can see that we are having 3 carbon atoms covalently bonding to one another. And this means that out of the 4 valency electrons, only 3 are used to form the covalent bonds. So only each carbon atom uses only 3 electrons in the outer energy level to form the covalent bonds. Each carbon atom, that is now about the structure of the graphite. And the structure of the graphite is such that each carbon atom only uses 3 valency electrons. It uses only 3 valency electrons to form the covalent bond. And when you're writing the electron configuration, we saw that it has got 4. So it means that out of the 4 valency electrons, only 3 participate in the formation of the covalent bonds. And this leaves it with 1 electron, which is delocalized. This leaves it with 1 delocalized electron. And because of this 1 delocalized electron, graphite is a good conductor of both heat and electricity. It's a good conductor of both electricity and heat. So this is the kind of question you find in exam. In terms of structure and body, explain why diamond is a non-metal, yet it conducts electric current. That is the correct response. That out of the 4 valency electrons, only 3 are used to form the covalent bonds, and this leaves it with 1 delocalized electron, and this one delocalized electron is the one that is responsible for the conductivity of heat and electricity. It's the one responsible for the conductivity of heat and electricity. That is the first property of graphite. It's a non-metal. It's actually the only non-metal that conducts heat and electric current. And the reason is due to how the structure is. Only 3 valency electrons participate in the formation of covalent bonds, and this leaves it with one delocalized electron, the one that is responsible for the conductivity of heat and electric current. The other property of graphite that I'm going to highlight on is on its density. The density of graphite is relatively low compared to that of the diamond. Graphite has a low density of around 2.3 grams per centimeter cube. Diamond graphite has a low density of 2.3 grams per centimeter cube. And this low density is due to the spaces between the layers. This low density is due to the spaces between the layers. Is due to the spaces between the layers. I've just drawn the hexagonal layers, and in between one layer and the other one, there were spaces. And these spaces count for the low density of the graphite. So in exam, this is the kind of question you find. Explain the low density of graphite. Explain the low density of graphite. The low density is due to the spaces in between the layers. The low density is due to the spaces in between the layers. The other property of the other property of the graphite that I'm going to discuss is on the softness and the slippery nature of the graphite. Graphite is soft and slippery. 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 So this is the kind of question you expect in the exam. In terms of structure and body, explain the slippery nature of graphite. In terms of structure and body, explain the slippery nature of graphite. The reason for it being soft and slippery is because the layers in the structure can slide over each other due to the weak van der Waals forces. The soft and the slippery nature of the graphite is because the layers can slide over each other. The layers can slide over each other due to the weak van der Waals forces. Due to the weak van der Waals forces due to the weak van der Waals forces. From the diagram, you've seen that the hexagonal layers are held together by the weak van der Waals forces of attraction. And these layers, when you slightly place them, they slide over each other because in between the layers, the force of attraction that exists is the weak van der Waals forces of attraction. In between the layers, the forces of attraction that exist is the weak van der Waals forces. The other point that we are going to discuss on the graphite is on the melting point and boiling point. The melting point and the boiling point of graphite. So graphite has got high melting point and boiling point. Graphite has high melting point and boiling point of around 35 degrees Celsius. Graphite has a high melting point and boiling point of around 35 degrees Celsius. And the reason for the high melting point and the high boiling point is due to the strong covalent bonds between the atoms in its layers. This is due to the strong covalent bonds. This is due to the strong covalent bonds between the atoms in its layer, between the atom in its layers, between the atoms in its layers. I've drawn the diagram and I've shown in between a carbon atom and another carbon atom, we have the strong covalent bond. And these are strong covalent bonds requires a lot of energy to break. And for this reason, the melting point and the boiling point of the graphite is high. The melting point and boiling point of graphite is high. From there, we're going to look at the uses of graphite based on the properties that we have. Uses of graphite based on those properties that we have highlighted. The uses of graphite based on those properties that we have highlighted. One use is it is used as a lubricant. One use of the graphite is that it is used as a lubricant. And so the examiner will bring this question. In terms of structure and body, explain why graphite is used as a lubricant. In terms of structure and body, explain why graphite is a lubricant. It is due to its slippery nature and the high melting point and boiling point. Graphite is used as a lubricant, and this is mostly in moving machine parts. In the moving machine parts, graphite is used as a lubricant. Reason due to its high melting point and its slippery nature. The other use of the graphite is that it is used as an electrode. it is used as an electrode. Again, in terms of structure and body, explain why graphite is used as an electrode. This is due to the presence of delocalized electrons in its structure. This is due to the presence of delocalized electrons in its structure. The other use of graphite is to make pencil leads. Graphite is used to make the pencil leads. Explain in terms of structure and body. So graphite once mixed with clay. It is mixed with clay, and then the mixture is used to make the pencil leads. This is because the carbon layers can slide over each other. This is because the carbon layers can slide over each other. This is because the carbon layers can slide over each other. And those are the properties and uses of the two pure allotropes of carbon. And to conclude on that, I want us to summarize and compare the physical properties of diamond and those of graphite. I want us to summarize all those in form of a table, the comparison of the physical properties between diamond and graphite. I'm going to summarize all that in terms of a table. I'm going to compare the two pure allotropes of the carbon. And we're going to have a column for the property. The other column is for the diamond, and the next one is for the graphite. So I want to summarize all those properties that I have discussed. The first property that I started with was on the appearance. The first property that I discussed on was on the appearance, and we've seen the appearance of the two. That one of a diamond, we said it is colorless and it is transparent, crystalline solid. It is a colorless, it is a transparent, crystalline solid. It is colorless and a transparent, crystalline solid. It is colorless, transparent, and it is a crystalline solid. That one of graphite, we see it's a black, it's opaque, solid, and has got a metallic structure. It is a black, it is a crystalline solid, it's a black crystalline solid that has got metallic structure. The next property that we have highlighted is on density, and we've seen that the density of diamond is relatively high. We've seen why. That one of graphite is bit low, 2.3 grams per centimeter cube. We've seen why. The other property is about the hardness, and we've seen that diamond is the hardest naturally occurring substance. It is the hardest naturally occurring substance. It is the hardest naturally occurring substance. While with graphite, we've seen that it is soft and slippery. It is a soft and slippery substance. Electrical conductivity is the other physical property that we have highlighted, and seen that with diamond, all the 4 valency electrons are used, and for this reason, it is a non-conductor. It does not conduct heat and electricity. With graphite, only 3 out of the 4 valency electrons are used. This leaves it with 1 delocalized electrons, and this makes it to be a good conductor of heat and electricity. We've also discussed about the melting point and the boiling point, and seen in both they are high reason the strong covalent bonds throughout their structures. The strong covalent bonds throughout their structure. So those are the 2 pure allotropes of the carbon. We also said that carbon can exist as an impure. It can exist as an impure substance. And this impure allotrope of carbon is known as amorphous. Amorphous is the impure form of carbon, and it's the one that we are going to discuss next. Amorphous carbon is the impure form of carbon, the amorphous carbon. The amorphous carbon is the impure form of carbon. So amorphous means without shape. So these ones are not crystalline. They are non-crystalline. Amorphous means without shape. Amorphous means without shape. And amorphous carbon is the non-crystalline solid. It's a non-crystalline solid. It's a non-crystalline solid. This amorphous form of carbon does not occur naturally, but it is made artificially in various forms. This amorphous form of carbon does not occur naturally, but it is artificially made. It is artificially made in various forms. So which are these main ones? Which are these amorphous forms of carbon? We have quite a number of them that I'm going to go through them. The first one is coke, C-O-K. It is an amorphous form of carbon without shape, non-crystalline, and artificially made. The other amorphous form of carbon is the wood charcoal. The wood charcoal is the other example of amorphous form of carbon. The third one is the animal charcoal. The third one is animal charcoal. Okay. There is someone there who is asking about silicon dioxide. That one is under structure and body. I will explain to you after this, I'll take you back to the topic of structure and body and explain to you about silicon 4 oxide. It is still a giant atomic structure, but kindly allow me in boxing after this lesson, I'll explain to you because we covered it under the structure and body. It's not an electron. So we move on to the next example of amorphous carbon. I've mentioned the examples of amorphous form of carbon as the coke, the wood charcoal. The other one is the animal charcoal, We also have the lamp black or carbon black. We also have the carbon black, also called the lamp black, also called the lamp black. And we have the next one is the sugar carbon. We have the next one as the sugar carbon. So these are the amorphous forms of carbons: the coke, the wood charcoal, the animal charcoal, the carbon black, also called the lamp black, and the sugar carbon. I'm going to discuss each one of them at a time on how it is artificially made, because I said they do not occur naturally, but they are artificially made and their uses. So I start with the first form of amorphous carbon, and that is the coke. I start with the first form of amorphous carbon, and that is the coke. How is the coke made? Coke is made by heating coal in absence of air. Coke is made by heating coal in absence of air. It is made by heating coal in absence of air. Commercially, coke is used as a fuel and as a reducing agent. We are going to come across this term once we'll be discussing extraction of metals in Form 4. And it's one of the major raw materials. You just come across it when we'll be discussing on the Sulby process. So it is used as a fuel, and it is also used as a reducing agent, which is made by heating coal in absence of air. And the uses: fuel and reducing agent, especially in extraction of metals from their ores, especially in extracting metals from their ores. You'll come across it quite a lot in the Form 4. Coke is also used to manufacture graphite. Coke, the other use of coke is to manufacture graphite. Coke is also used in the manufacturing of graphite. It is made by heating coal in absence of air, and that's when we are saying it is impure and a form of carbon that is artificially made. The other form of amorphous carbon is the wood charcoal. The second example of the amorphous form of carbon that I gave is the wood charcoal. We are all familiar with the wood charcoal, makaa. This one is made by heating wood in a limited supply of air. This one is made by heating wood in a limited supply of air. It is made by heating the wood in a limited supply of air. What are some of its uses? All of us are familiar with it. It is used as domestic fuel. It is used as a domestic fuel. It is also used as absorbent material for toxic gases in industry. It is used as an absorbent material for toxic gases in industries. For toxic gases in industries. Charcoal is also used to make the gas mask commonly used by miners. It is used to make the gas mask commonly used by the miners. The charcoal is an amorphous form of carbon made by heating wood in limited supply of air and has got various uses. Domestic fuel, absorbent material for toxic gases in industries, and gas mask, which is used by miners. The third amorphous form of carbon that I mentioned was the animal charcoal. The animal charcoal was the third amorphous form of carbon, the animal charcoal. Animal charcoal is made by heating bones in a limited supply of air. Animal charcoal is made by heating bones in a limited supply of air. In a limited supply of air. What is the major use of the animal charcoal? This one is used commercially for decolorizing sugar. It is used commercially to decolorize sugar. To decolorize sugar, that is turning it from brown to white. That is turning it from brown to white. That is the main purpose of the animal charcoal made by heating bones in a limited supply of air. The other example of amorphous carbon that I mentioned was the lamp black or the carbon black. The lamp black or the carbon black. The lamp black or the carbon black. This one is made by burning hydrocarbon gases, tar, or oil. It is made by burning hydrocarbons. We came across the word hydrocarbon in Form 1. It's a compound made up of carbon and hydrogen atoms only. So when these hydrocarbon gases are heated in a limited supply of air, the result is the carbon black, the lamp black. So lamp black is made by heating or burning the hydrocarbon gases, by heating the tar, or by heating the oil in limited supply of air in limited supply of air, whereby it is deposited as the fine soot. It is made by burning hydrocarbon gases, the tar or oil in limited supply of air, whereby it is deposited as fine soot, whereby it is deposited as fine soot. What are some of the uses of this carbon black, this lamp black? It is used to reinforce rubber, especially for the tires and the footwear. It is used to reinforce the rubber for tires and the footwear. It is used to reinforce the rubber, which are used to make the tires and the footwear. It is also used to make the black pigment in the printing ink. It is also used to make the black pigment in printing ink. In printing ink, it is also used to make the black pigment in the shoe polish, and it is also used to make the black pigment in paint. It is also used to make the black pigment in the paint. So that is about the lamp black, the carbon black, which is made when hydrocarbon gases, when the tar, oil, or oil are heated in limited supply of air, resulting to deposit of the fine soot. And this fine soot is the one we are referring to as the lamp black or carbon black, whose uses are so many: reinforcing the rubber, which is used to make the tires or the footwear, to make the black pigment, which is used to make the printing ink, to make the black pigment, which is used to make the shoe polish and the paint. I move on to the last form of amorphous carbon. We look at the last form of amorphous carbon, and this is the sugar carbon. And this is the sugar carbon. Sugar carbon is made by heating sugar in absence of air. Heating sugar in absence of air. Sugar carbon
Madam Ann, microphone yako. Sikii.
Hello? Hello?
Na sasa uko sawa?
Umetoka mbele.
Hello? Hello?
Tunakusikia sasa.
Okay, I continue.
Yeah.
Sorry for the disruption. I was discussing on.
You switch off your camera and you're using
I
it.
switch on.
You
Hello?
have switched off the camera. You have switched off your camera.
Nimeswitch off the camera.
Sorry for the disruption. I was discussing the last amorphous form of carbon, and that is the sugar carbon, which I was discussing how it is made. And I said it's made by heating sugar in limited supply of air. And it can also be made by dehydrating sugar using concentrated sulfuric acid. What do we mean when we talk of dehydrating sugar? Dehydrating is removing the water or elements of water. Dehydration means removal of water or elements of water or elements of water from substances that contains it. When we talk of elements of water, we are talking of the hydrogen and the oxygen. So if you remove hydrogen and oxygen from a substance that contains it, that process is called dehydration. Even if you remove the whole hydrogen and oxygen combined to give water, that is also called dehydration. And that is the second method of preparing the sugar carbon, which is an amorphous form of carbon. Either you heat sugar in absence of air, or you dehydrate sugar using concentrated sulfuric acid. And from that, I would like to give us some questions to assess ourselves on what we have so far understood. I want us to look at some questions up to where we have covered. So let's test our knowledge so far before we continue. The first question that I would like you to answer is, define the term allotrope. Define the term allotrope. Define the term allotrope. The second question is, give two allotropes of carbon. Give two allotropes of carbon. Give two allotropes of carbon. Next, state two properties of one of the allotropes of carbon you have mentioned above. State two properties of one. Someone is asking why we use calcium hydroxide to test carbon dioxide, which is in the next content. The next subtopic will be on the properties of the carbon, which you are going to look at how it is confirmed, how its confirmatory test is carried out, and what we use and why we use it. So just hold on. The next concept, I've seen that question being raised. It's in the next thing that we are going to learn. So the question I was giving was state two properties of one of the allotropes of carbon you've named above. The next one is explain how the allotropes is used due to its properties named above. Explain how the allotropes you mentioned above is used due to its properties. Due to its properties. Explain how the allotropes you have mentioned above is used due to its properties. The next question, differentiate between diamond and graphite. Give yes, Larry Gekonyo, that is very good. The answer is very correct. I agree with you. You've defined allotropes as elements that exist in more than one form in the same physical state. That is very good. So the other question, I'm not yet done with the question. The other question is give the differences between the two pure allotropes of carbon, that is diamond and graphite. That is diamond and graphite. The other question is state 3 uses of diamond and 3 uses of graphite. State 3 uses of diamond, graphite, and amorphous carbon. If there is any challenge, yes, I can see. Okwaro, just I've not seen your question clearly. Repost it so that I can address it. Would you pardon the uses of sugar carbon? Yes, I'll repeat on the uses of sugar carbon. Sugar carbon is used to absorb gases in chemical processes. Sugar carbon is used to absorb gases in chemical processes. Yes, I can see 842 telling us on uses of diamonds. Some people cannot see the charts. That is from the central part, but I'm reading all of them. So be keen. I'm waiting on the response to these questions that I've given you. Diamond is a poor conductor of heat and electricity, while graphite is a good conductor of heat and electricity. That is to do with the differences between the two. Someone is requesting that I repeat on coke. So I'll repeat on how it is made. Yes, is it correct to say that fullerene is an allotrope of carbon? That is correct. Initially, I said some of these allotropes of carbon can be altered by subjecting them to heat. And once you alter them by subjecting to heat, you get the fullerenes or the buckets So you are very correct. You are very correct. Can also report fullerene as an allotrope of carbon. Another one. Is there another use of diamond other than for drilling and used to make jewels? Sugar carbon can be formed. But diamond has no delocalized electron, but graphite has delocalized electrons. That is correct. I think you are addressing on the differences. But which look is the most suitable for chemistry books? I'll answer all those. At the end of this, some of those questions that you're asking needs individualized attention are addressed to all of them. But from the response of what I have discussed, I can see that we've understood that part. So allow me to move on to properties of carbon. There are many, we may not finish all of them, but allow me to just discuss the ones that I'll be able. The use of the animal charcoal. It is used commercially to decolorize sugar, to turn it from brown to white, turning it brown to white. So if there's no other question on the areas that I've discussed, kindly allow me to sugar carbon. What about sugar carbon? What do I say? I repeat about it. Sugar carbon, I've said, is made by heating sugar in absence of air. It can also be made by dehydrating or removing the elements of water or water from sugar using concentrated sulfuric 6 acid. And it is used to absorb is used to absorb gases in chemical processes. It is used to absorb gases in chemical processes. Someone is also insisting on coke, and I've repeated on that. And I said that coke is made by heating coal in absence of air, and it is used commercially as a fuel, and it is used as a reducing agent during extraction of metals from their ores. So I think it is also used to make graphite. I think so far we are okay. Can I move on to the properties of carbon? Now we know what is carbon, the chemical table, where you can find it in the periodic table, the occurrence of some of those questions you are asking, I'll not respond to them. The occurrence of carbon and the existence. We've seen how it occurs as a pure form, as in pure form, and we've discussed all those and their uses. And so I move on to properties of carbon. Remember when I started the topic, I said this topic has been split into two, carbon and its compounds. So we are still on carbon. Hatujaenda kwa the compounds of carbon. So the only thing we are left with, the carbon, is on the properties of carbons, which I'm going to move on to. The properties of carbons, they are many. I may not exhaust all of them today, but we can just handle where we can the properties of carbon. Properties of carbon. Now we know what is carbon. Where can we find it in the periodic table? How does it occur? Which are these allotropes of carbons? What are their properties? What are their uses? There are some people who are still posting other questions there. Let's move on to the properties of carbon. Properties of carbon will be our next subtopic. There are so many, but allow me to discuss even if it is one. Properties of carbon. Properties of carbon. Properties of carbon. The first property that I am going to discuss is on how it reacts with oxygen. Reaction of carbon with oxygen. Reaction of carbon with oxygen. Reaction of carbon with the oxygen. I'm going to diagrammatically show how this area can be tested in exam. we've got a diagram here, and this diagram represents a defragerating spoon. It represents a defragerating spoon. The work of the defragerating spoon is to heat substances when they are being burnt. So the examiner may decide to draw this defragerating spoon. And here we have got charcoal. We have got our charcoal. Charcoal is an amorphous form of carbon. You have animal charcoal, you have the wood charcoal. You've seen how they can be prepared. And this charcoal is being heated. There is heating that is taking place. So after this charcoal has been heated, it is transferred into a gas jar. And this gas jar is full of oxygen. This gas jar is full of oxygen. It is full of oxygen. I have the gas jar here, and this gas jar is full of oxygen. This is gas jar, and inside this gas jar, it contains oxygen. Gas jar containing oxygen. And we bring in our burning charcoal. We are bringing in our burning charcoal. And this is the first kind of a question you may expect from such kind of a diagram. State and explain the observations made when the hot charcoal is transferred into the jar, into the gas jar containing oxygen. That is how normally the examiner assesses this area. State and explain the observations made when this charcoal, which is hot, we heated it, is transferred into a gas jar that contains oxygen. So what are some of the observations that are made when you transfer the hot charcoal into this gas jar containing the oxygen? So this is the observation. The hot charcoal continues to burn with yellow flame even without further heating. You can see in the gas jar, there's no heating. But once you transfer the hot charcoal into the gas jar that contains oxygen, it continues to burn slowly with yellow flame. The hot charcoal continues to burn slowly with yellow flame. That is the observation, what you can see. The hot charcoal continues to burn slowly with yellow flame, even without any further heating. The hot charcoal, once transferred into the gas jar that contains oxygen, it continues to burn slowly with yellow flame. This shows that the reaction between charcoal and oxygen releases heat. The fact that the hot charcoal continues to burn even without further heating is an indicator that the reaction between the burning charcoal and the oxygen is exothermic. It releases heat. This shows that the reaction is exothermic. Exothermic means that heat is evolved. heat is given off. And this is why it will continue to burn without further heating. And this production of heat by burning charcoal explains why it is used as a fuel. This production of heat by burning charcoal explains why we use charcoal as a source of fuel. That is the first observation, that when we remove the hot charcoal and transfer it to the gas jar that contains oxygen, it still continues to burn even without further heating, indicating that when charcoal and oxygen are burning, there is heat which is being released. The reaction is exothermic. And for this reason, charcoal is used as a fuel. The other observation that will be made on transferring the hot charcoal into the jar containing the oxygen is that the amount of charcoal gradually decreases, and finally, a small amount of ash is left. The second observation is that the amount of charcoal gradually decreases, and finally only a small amount of ash is left, and only a small amount of ash is left, and small amount of ash is left. This presence of ash shows that the wood charcoal is not a pure form of carbon. The presence of ash shows that wood charcoal contains impurities. The presence of ash shows that wood charcoal is not a pure form of carbon. It contains impurities. This was a question that I was asked, when calcium hydroxide, which is also called lime water, is put into the gas jar, a white precipitate is formed. I'm responding to one of those questions that had been earlier asked, that when we add lime water is calcium hydroxide solution. When we add it to the gas jar, to the ash that was formed, the white precipitate was observed. There was formation of white precipitate. And this is an indicator that charcoal burns in excess oxygen to form carbon dioxide. This shows that carbon burns in excess oxygen to form carbon dioxide. The examiner may still tell you to write the chemical equation for the reaction that takes place in the gas jar. We have our charcoal, which is carbon, an impure form of carbon, burning in oxygen, which is a gas, and it is in excess oxygen. So it undergoes complete combustion, that is leading to the formation of carbon 4 oxide. And you see that the reaction is exothermic. Heat is being evolved. So we add plus heat there. If this wood charcoal was being allowed to burn in limited supply of air, the products would not be carbon 4 oxide, but carbon 2 oxide. If this oxygen, this one was excess, that's why we have carbon 4 oxide being formed, because carbon undergoes complete combustion in limited amounts of oxygen. If the amount of oxygen here is limited, we would end up with carbon 2 oxide and heat. So the examiner may tell you if this was done in excess or in limited amounts, write a balanced chemical equation for the reaction that will occur. So that will be the equation. And that is one of the property of carbon and how it reacts with oxygen. In the presence of oxygen, it continues to burn even without further heating. And this is an indicator that the reaction is exothermic. And for this reason, charcoal is used as a source of fuel. The other observation is on the amount or the quantity of charcoal. It gradually, yes, if it is showing, yes, you must include heat when you are burning. When you are burning, include heat. So that is about how charcoal burns in the air, the first property of carbon, the first property of carbon. So I'm going to post some questions which will be posted on your wall. You can try to go through them before we meet in our next lesson. Thank you for your patience and your active participation. Until next, bye.